Do you feel like your heart just might explode because you glanced down at your math homework and noticed that your teacher just happened to include a fraction and a decimal in the same math problem? Outstanding. We can help you avoid cardiac arrest in a Saturday afternoon funeral by watching this here video by Fort Bend Tutoring and Mr. Whitt.
Hello, ladies and gentlemen, this is Mr. Whitt with Fort Bend Tutoring, and today's tutorial is going to be about nonlinear systems. That's right, we'll be dealing with systems that do not contain lines, or at least some of them won't have lines in them. There may be a few with lines, but one thing's for sure, the system won't contain two lines. So this won't be linear systems. This may be a line and a parabola. This may be a parabola and a circle. It may be a circle and a circle. You see what I'm saying? You see where I'm going with this? Bottom line, nonlinear systems. That's what's going to be coming up for you today. And we have a snapshot of the problems that we'll be covering. Number 1, number 2, number 3, and there you go, number 4. However, there are actually 5 problems in this video. And as a bonus, we'll be verifying each one of our problems with the TI-Nspire CX CAS from Texas Instruments. Oh yes, it's going to be fun today because we'll be utilizing some of the unique functions of the TI-Nspire CX CAS, not only to showcase some of the many functions that this calculator has, but also to show you how to use it as a tool to enrich your mathematics foundation, as well as your academic endeavors in mathematics. All right. So it's going to be some fun times between Texas Instruments, Fort Bend Tutoring, and you right now. Let's go ahead and get started with problem number 1. All right, in problem 1, we have x squared minus 2y equals 10, as well as 3x minus y equals 9. Well, the first function will be a vertical parabola, and the second equation is a linear function. So what we're looking for is the potential intersection or intersections between these two functions. So using the TI-Nspire CX CAS, not only will I be showing you how to find the solution using the calculator, but in addition to that, we're going to also show you what the graph looks like using the TI-Nspire CX CAS. First and foremost, let's see what you can do in order to solve this problem. So I'm thinking the best approach to this problem is going to be using substitution. So I'm going to take the linear function, the 3x minus y equals 9, and I'm going to solve for y. All right. So we have 3x minus y equals 9. So solving for y, we'll be subtracting 3x to both sides of the equal sign using the subtraction property of equality. Our 3x's will cancel out. We'll be bringing down negative y, which equals negative 3x plus 9. From here, we'll be dividing each and every term by negative 1 in order to solve for a positive 1y, and therefore we end up with a positive y equals 3x minus 9, and this is going to be our value for y that we'll be able to plug in to the first equation. In fact, it's going to look just like this. We'll have x squared minus 2 times the quantity of 3x minus 9 equals 10, just like that. And from here, we will get our arrows popping. That's right. Go ahead and circle that negative to remind you that you're distributing a negative value into the parentheses, and distribute the negative 2. Distributing the negative 2 will end up with x squared minus 6x plus 18 equals 10. From here, I'll be subtracting 10 to both sides of the equal sign in order to set the equation equal to 0. We'll have x squared minus 6x plus 8 equals 0. And now we'll be solving our quadratic equation using the zero factor property. So if you need a refresher over the zero factor property, go ahead and check out this link right here. Okay, there you go. So factoring our quadratic equation, we're looking for 2 factors of 8 that will add to give you 6. So if you're looking at the factors of 8, we have 1 times 8, we have 2 times 4, and lo and behold, it's 2 times 4 that'll multiply to give us 8, but will also add to give us 6. If you need some additional practice on factoring quadratic trinomials, go ahead and check out this video right here. There you go. We got you. Okay, here at Fort Bend Tutoring, yeah, we have you. Thank you. We're going to factor this. This becomes x minus 4 times x minus 2 equals 0. Yeah. And because I'm using the zero factor property, I know I can take each one of these factors and set them separately equal to 0 and get a potential value for x. Oh, yes. So we'll have x minus 4 equal to 0. We'll have x minus 2 equal to 0. In solving for each one of our equations, we will be adding 4 to both sides of the equal sign. This gives us x may equal to 4, and adding 2 to both sides of our equal sign as well, we'll have x equals 2. So once again, these are potential solutions. The reason why we're saying that they're potential solutions is because some of these equations may end up with extraneous solutions, meaning that they won't work in the original problem. Therefore, we're going forward with these values of x, assuming that they will work. But of course, you'll need to verify that the solutions that you obtain throughout your process works in the original equation. And remember, in order to verify a solution for a system of equations, the solution must work in every equation within the system. So now we know that x may equal to 4 and x may equal 2. Remember that this is a point on the Cartesian plane, so we'll need an x and y value. Remember that we isolated y in the beginning, and we said that y was equivalent to 3x minus 9. So knowing that y is equal to 3x minus 9, we'll be plugging each one of these values of x into our equation where we isolated y and find out the value of y for the respective value of x. All right, so let's do just that. When x is 2, we'll have y equals 3 times the quantity of 2 minus 9, and 3 times 2 is always 6, so we'll have 6 minus 9, and so y may equal negative 3. So as an ordered pair, when replacing x with 2, you'll end up with the intersection 2, negative 3. Once again, I still need to verify this by ensuring that it works in the original system in both equations. So for right now, the 2, negative 3 may be one of the intersections of these two functions. Now let's see what happens when we plug in 4 for x. So plugging in 4, we'll have 3 times 4 minus 9, and then simplifying this, the product of 3 and 4 is 12, so we'll have y equals 12 minus 9, and then as a result, we have y equals 3. So one of our potential solutions is 4, 3. All right, so we have 2, negative 3 as a potential point of intersection, and we also have 4, 3 as another potential intersection point. So let's go ahead and plug these in to see if they work. So verifying the point 2, negative 3, we'll be replacing the x's with 2 and then replacing the y's with negative 3. So now that we've replaced those values, 2 squared is 4, negative 2 times negative 3 is positive 6, and since 4 plus 6 equals 10, then this works just fine for the first equation. However, just because our point works in the first equation doesn't mean that it may work in the second one. We have to verify that the point works in every equation within the system. So plugging in 2, negative 3 into the linear function, we'll have 3 times 2 minus negative 3 equals 9. All right, so now multiplying the 3 times 2, you'll end up with 6 plus 3 equals 9. And yes, ladies and gentlemen, 9 equals to 9. So therefore, we know for certain that 2, negative 3 is a solution to this system. Now let's try 4, 3. Let's see if that works. So replacing all the x's and y's with 4 and negative 3 respectively in our original system, we'll have 4 squared minus 2 times 3 equals 10. Well, we know that 4 squared is 16, and 16 minus 6, yeah, well, that does equal to 10, doesn't it? So therefore, the first equation works just fine with the point 4, 3. Now let's try that in our linear function. We'll have 3 times 4 minus 3 equals 9. So we know that 3 times 4 is 12, and 12 minus 3 is 9. Ladies and gentlemen, looks like we found the two solutions for this system. Those points are, once again, 2, negative 3, and we also have the point 4, 3. Yeah, I know that's an ugly 4. I'm gonna fix it. I'm sorry. I don't know what happened, but I'm fixing it. I'm fixing it for you. There you go. All right, so that's just as ugly. I'm aware of that. We're going to keep it. We're going to keep it. We're going to keep it. Thank you. And now, because this is our solution, ladies and gentlemen, red box it. Red boxing it, ladies and gentlemen. And that's the solution for number 1. So that's how to find the solutions to this system by hand. Now let's see what our trusty TI-Nspire CX CAS can do. All right, here we go. So what we'll be using within this video is the TI-Nspire CX CAS student software that comes free with the purchase of the calculator. So the two things that we'll be showing with each problem is one, how to simply solve the equation using the TI-Nspire CX CAS, and then two, how to find our solutions by graphing the system. So we'll begin here by going to our calculator, and from the scratchpad screen, we'll go ahead and type in our first problem. We'll go ahead and access the menu, and then go to algebra, and then from algebra we'll go to solve systems of equations, and we're going to choose to solve a system of equations instead of solve system of linear equations because we know that we are dealing with nonlinear systems. So we're going to choose this first option. We have two equations. Our variables are x and y, so we'll go ahead and click OK. So we're clicking the area for our first equation, and our first equation will be x squared. Then we have minus 2y, and then the equal sign and 10, and that completes our first equation. And then for our second equation, we'll click on this second box here, and that takes us to the second area where we can input our second equation, which is going to be 3x minus y equals 9, and then we'll hit enter. And right there we have the solution to our system. It's just that simple. So we have our first point, which is going to be 2, negative 3, and we have our second point, 4, 3. And that's it. It's just that fast. So because of TI's CAS technology, which stands for Computer Algebra System, we were able to get our points of intersection from these two functions using the CAS technology in our TI-Nspire CX CAS. And this is just a student software. You can do the exact same thing, obviously, on the calculator itself, but the software allows you this capability to showcase your work for your instructor or to a classroom. And it's an ideal way to check your work as you're doing your homework, preparing for a test, or even as a parent that's trying to check your child's work. You don't necessarily need to know the complete process to solve the problem. You can simply use this calculator to check your child's work and make sure they're doing it correctly. Okay, let's go ahead and see what the graph of the system looks like on the calculator, all right? We're gonna go ahead and click on the home button here, and from the home button, we'll go to where it says graph. Now from our F1 of X prompt, we'll be putting in each one of the equations, and mind you, these equations need to be solved for y when you're inputting it into this section of the calculator. 1/2 x squared minus 5, and that's going to be for our first equation. And then we'll go ahead and add the second function by going to menu, and then under graph entry we'll go to one function, so that gives us another prompt. Notice it says F2 of X. Now we'll input the second equation. Once again, we need to solve for y to input it, so we'll input it in as 3x minus 9, and then we'll hit enter. And that shows us our second graph. So what we want to find now is the 2 points of intersection. So what we'll do from here is we'll go to menu, and then we want to go to analyze graph, and we want to go to number 4 where it says intersection. So then from here we're going to click our lower bound, and we'll try it about right here, and we'll slide over. And notice how it says intersection now, that it found an intersection. We'll go ahead and click again to give us the upper bound, and it'll give us, all right, here we can move it. Let's see. It'll give us that intersection of 2, negative 3 that we found. All right. So that's one of the intersections. And so we'll repeat that process to find the second point. So finding the second point, we'll once again click on menu. We'll go to analyze graph. We'll go to 4, which is intersection, and then we'll create the lower bound by clicking to the left of where we think the intersection is, and then moving over to it says intersection where it finds one, and clicking for the right, and notice how it found our second point, 4, 3. So here's the graph of those two functions. Notice once again we have the linear function, we also have the quadratic function, and we found the 2 points of intersection where we can see where these two functions intersect, and that confirms our answer for problem number 1. Let's move on to the next problem. In problem 2, we have a rational function with xy equals 6, and we also have another linear function in 2x minus y equals 1. Once again, I'm going to go ahead and use substitution. So I'm going to go ahead and start with the second equation, the linear function, and solve for y. So I'll take 2x minus y equals 1 and subtract 2x to both sides of the equal sign. From here we have negative y equals negative 2x plus 1, and then I'll divide each and every term by negative 1. Simplifying our equation, we have y equals 2x minus 1. And because we know now that y equals 2x minus 1, we'll be substituting in this value of y into our rational function. So we will rewrite the rational function as x times 2x minus 1 equals 6. And then from here, I will get my arrows popping. Thank you. So I got my arrows popping here. I'm in heaven. Thank you. After distributing your value of x, you'll end up with 2x squared minus x equals 6. Well, once again, we end up with a quadratic equation. So let's go ahead and set it equal to 0. So I'll subtract 6 to both sides of the equal sign and end up with 2x squared minus x minus 6 equals 0. From here, I'll attempt to use the zero factor property. So my hope is that we'll find a product of our A and C coefficients that will have factors that will subtract to give us 1. So by multiplying 2 times 6 here, you'll end up with 12. And looking at factors of 12, we have 1 times 12, 2 times 6, we have 3 times 4, and 2 factors of 12 that will also subtract to give you 1 will be 3 and 4. So if you want to see more examples of how to factor trinomials of this type, go ahead and check out our Factoring Quadratic Trinomials Part 2 video, and I'll even put in a link right here. Go ahead and click on that. Thanks. Appreciate it. It'll help you. Okay. So knowing that I'm going to use 3 and 4 as my factors, I'll set up 2 sets of parentheses here, like so, and I'll say that I have my variable x as the first term in each set of parentheses, and I'll be using 4 and 3. Because the middle term's coefficient is negative, I know that the largest factor must be negative, and because we're subtracting to get a value of 1, I know that the other factor must be positive. From here, because of this leading coefficient of 2, I'll be dividing each value here by 2. Next, I'll be simplifying, so we end up with x minus 2 times, and then because I can't simplify that 3 halves any further, this denominator will go in front of the variable, and I'll end up with 2x plus 3 equals 0. And now we have the factorization of our original trinomial here that will multiply to give us back that 2x squared minus x minus 6 equals 0. Because I have my equation fully factored, I can now set each factor equal to 0 to solve for my potential values of x. So let's do just that. We'll have x minus 2 equals 0. We'll also have 2x plus 3 equal to 0, and then I'll solve for x in each equation. So in the first equation, I'll be adding 2 to both sides of the equal sign using the addition property of equality. So x may equal 2. In the second equation, I'll be subtracting 3 to both sides of the equal sign, and so I'm bringing down 2x, and I'll bring down that negative 3, and then from here, I'll be dividing both sides by 2. Dividing both sides by 2, we find that x may equal negative 3 halves. All right. Recall that during the process, we isolated the variable y. Well, we'll be using that equation to solve for our potential values of y. So we stated earlier that y equals 2x minus 1, right? So now we'll be plugging in negative 3 halves and 2 respectively in order to solve for y. Plugging in negative 3 halves, we'll have y equals 2 times negative 3 halves minus 1, and then simplifying this because our 2's will cancel out, we'll have negative 3 minus 1, which equals negative 4. Yeah. So that means that one of our intersection points may be negative 3 halves, negative 4. All right, because we replaced x with negative 3 halves, and our end result was negative 4 in this case. So this may be one of our points of intersection. Now let's plug in positive 2. So we'll have y equals 2 times 2 minus 1. This equals 4 minus 1, and that means that y may equal to 3. So as a second point of intersection, we will end up with 2, 3. So these 2 points will be the 2 points that we'll need to verify in our original system. Remember, in order for these points to actually be a solution to the system, the x and y values of the point must create a true statement in every equation within the system. So testing these 2 points in our original system, we'll have negative 3 halves times negative 4 equals 6. So simplifying this, 2 goes into 4 twice. So negative 3 times negative 2 equals positive 6. So This works out just fine. However, the point must work in both equations. So that means that we'll need to plug this point, -3/2, -4, into the second equation to see if it works as well. So we'll have 2 times -3/2 minus -4, and this must equal 1. So simplifying before I multiply, I know that the 2's will cancel out and I'll be left with -3. The opposite of -4 is +4, and -3 plus 4 does equal to 1. So this checks out as well, which means that -3/2, -4 is definitely a solution to this system of equations. Exciting. So now let's plug in the values for my second potential point of intersection. All right, so testing 2, 3 in the first equation. 2 times 3, does this equal to 6? Yeah, it does. It does. It does. It does. It works. It does. You see it right there. Thank you. That works in the first equation, but the point must also work in the second equation. So we'll have 2 times 2 minus 3 equals 1. Well, we know that 2 times 2 equals 4, right? So this will be 4 minus 3 equals 1, and 4 minus 3, it equals 1, guys. It equals 1. Therefore, 2, 3 is a solution to this equation. Let's go ahead and write our answer. We'll have the point -3/2, -4, and the point 2, 3. They both work in the original system, and therefore they're both the answers to this problem. Red boxing it. And that's right, protecting our answer from the evil villains that would try to take it away. There you go. That's problem number 2. And now, once again, hey, Texas Instruments, what you got on this problem? For our second problem, we'll begin by hitting the menu button. We'll once again go to algebra and then solve system of equations. We once again have 2 equations. We'll click OK, and then we'll input our information for our second system. So notice that we have our 2 equations typed in, and all we have to do now is hit enter. So after inputting our equation into the calculator, we end up with our points of intersection, which are -3/2, -4, as well as 2, 3. Please make note that you must put in a multiplication symbol in between the x and the y here. So it won't automatically assume that these 2 variables are multiplying together unless you tell it to. So make sure after you input your x here, you'll have to put times and then the y, and then go ahead with the rest of your equation. It will expand a coefficient in a variable. So notice I just put in 2x, and then the calculator will automatically expand it into 2 times x, but it will not do that when you type in xy. So you have to manually type in x, then the multiplication symbol, then y when you're inputting your functions. All right. So we've confirmed that our points of intersection are correct by the CAS system. Let's go ahead and see what the graph looks like. So inputting our first equation from our system, I typed it in as y equals 6 divided by x. And then we'll go ahead and input the second equation as 2x minus 1, and then hit enter. And now we'll find our points of intersection. All right, so that's when we go to menu. We want to go to analyze graph, and number 4 is intersection. We're going to take our cursor here. We'll click to the left of the first intersection for the lower bound, move to the right till it says intersection. And then after you click, it'll give you your points of intersection. I'm gonna go ahead and move that over here. We end up with -3/2 and -4 for that first point. So that confirms that by the graph. And then to find the second intersection, once again, go to menu, analyze graph, go to intersection. We'll locate the second intersection by clicking to the left of that second intersection for our lower bound, and then move to the right until it says intersection as it does here, and click to the right of that intersection, and it'll find our second point of intersection. So here I can move that, and it shows us that our second point of intersection is at 2, 3. And this confirms our result for problem number 2. Let's move on to the next problem. That's right. Using the TI-Nspire CX CAS to assist us in this video. Hey guys, did you guys know that I'm a Texan? Born and raised in H-Town, aka Houston, Texas. You got it. Born and bred. Just like Texas Instruments, Tejas. You know what I'm saying? So here we go with problem number 3. We have y equals the negative square root of x minus 1, and we also have the quantity of x minus 3 squared plus y squared equals 4. So what we'll be doing in this problem is, once again, doing a bit of substitution. So since our first equation already has y solved for, we're going to use that in the second equation. Yeah, we're going to do that. And by the way, this is a square root function and a circle that we're trying to find the potential intersection of. All right, so let's check it out. Oh, yes. We're going to rewrite this as x minus 3 squared plus the quantity of negative square root of x minus 1 squared equals 4. It's beautiful. So once I've done this, we'll then expand that quantity squared to read x minus 3 times x minus 3. Just taking my time with it. That's all I'm doing. And knowing that we have this negative square root of x minus 1 squared, that a negative times a negative is a positive, and then squaring the square root, so it'll just be the radicand that remains, we'll have x minus 1 coming from underneath that radical. Oh, yes. And this still equals to 4. That's what's going on. So once again, the reason why we were able to eliminate the negative is because this is technically negative 1 squared, which is positive 1. And then the square root and the square would cancel out to leave us what remained, which was the radicand, which is x minus 1. And brought it down. From here, thank you, I will be getting my arrows popping as I distribute and multiply x minus 3 times x minus 3. Arrows popping. That's right. And now I'll multiply this out. So we'll have x squared minus 3x plus 9 plus x minus 1 equals 4. From here, we'll just go ahead and combine our like terms. So we'll have x squared. This is going to be negative 5x plus 8 equals 4. Next, I'll want to set this equal to 0. So that means I'll be subtracting 4 to both sides, like so. And I'll end up with x squared minus 5x plus 4 equals 0. Now, hopefully, at least I have my fingers crossed on this. The fingers they're really crossed. Thank you. I want this trinomial to be factorable. And I believe it is, because if you look at the factors of 4, we have 1 times 4 and 2 times 2, right? We're looking for 2 factors of 4 that will add to give us 5. Well, that's 1 and 4, right? It's 1 and 4. I'm excited. We'll end up with x minus 4 times x minus 1. It's because I'm lazy. I didn't want to do any extra work like the quadratic formula or the or the completing the square. Who wants to really do that? Not me. And by the way, if you do want to see that type of that type of problem where I do end up having to do the quadratic formula or completing the square to go further in the problem dealing with nonlinear systems, then you can check out our video. Matter of fact, here's one of the two. It will be a link right here. It's called Solving Exponential Systems. You'll see some of the madness that you so desperately need in your life. Thanks. But for this video, it's factorable. Yay. So therefore, I'll be setting each one of these factors equal to 0 and solving for x in each equation. So setting each one of our equations equal to 0, we'll have x minus 4 equal to 0, we'll have x minus 1 equals 0, and then we'll be solving for x. So in the first equation, I'm just going to add 4 to both sides, and that'll give me x equals 4. In the second equation, I'll add 1 to both sides of the equal sign. This gives me x equals 1. So these are our potential values for x. And now we'll be plugging these values into our original equation where we had y solved for. And that equation is y equals negative square root of x minus 1. So let's test x equals 4 and x equals 1 into both of these equations to see if we can solve for our value of y. Let's start with 1. Here we'll have y equals negative square root of 1 minus 1. This gives us y equals negative square root of 0, and that gives us y equals negative 0, which is not a number, so we'll just keep it at 0. Thanks. Yeah, it's just 0. I mean, you could say that this was equivalent to negative 1 times 0, and then that product is 0. Maybe that'll be clearer than using this right here. Yeah, that's ugly. Yeah, we won't use that. That's not a number. All right, so yeah. Here we have it. We have y equals 0. There you go. So that means that our intersection, our potential intersection, is going to be the point 1, 0. I hate the 0. We're gonna fix that. We're gonna fix this 0. It looks ugly. I think I can do better. Yeah, that's a better 0. Thank you. All right, so this is one of our potential intersections. Now, let's go ahead and plug in 4 for x and solve for y. We'll have y equals negative square root of 4 minus 1, which simplifies to give us negative square root of 3. So negative square root of 3 is another value of y that we may use. So that means that our potential point here would be 4 negative square root of 3. Yeah. And we'll be testing both of these potential intersections in the original system to see if there are solutions to our problem. So let's check it out. Well, let's start by looking at what appears to be simple first, which is the 1, 0. Let's see what happens when we plug that in. So we'll replace all the y's with 0, all the x's with 1. We'll have 0 equals the opposite of the square root of 1 minus 1. Well, ladies and gentlemen, 0 will equal to 0 in this case. Yeah, so that checks out. 1 minus 1 is 0, the square root of 0 is 0, and then the opposite of 0 is still 0, thank you. So therefore, this works. Yeah, it works. And it needs to work in both equations, though. So let's try the second equation now. Testing the point 1, 0 in the second equation, we'll have the quantity 1 minus 3 plus 0 squared equals 4. Well, we know that 1 minus 3 is negative 2, right? So this is going to be negative 2 squared plus 0 equals 4. And this gives me 4, which equals 4. And that checks out. So 1, 0 is definitely a solution to this system. Nice. Very nice. Let's go ahead and try the second point. With our second point, we have negative square root of 3 equals the opposite of the square root of 4 minus 1. Simplifying that 4 minus 1, we'll have negative square root of 3, which equals to negative square root of 3, and this checks out. It checks out just fine. Yeah, it does. So now let's go ahead and see if this works in our second equation. With the second equation, we'll have 4 minus 3 squared plus the quantity negative square root of 3 squared, and this must equal 4. Well, we do know that 4 minus 3 is 1, so that's 1 squared plus, and then we'll just bring down this negative square root of 3 squared for now. We're just going to bring it down. We're going to take our time. We're going to take our time. Thank you. 1 squared is 1 plus negative square root of 3 times negative square root of 3. It's just 3. Ladies and gentlemen, 4 equals to 4. This checks out just fine. That means that your solution for problem number 3 is the point 1, 0, as well as the point 4, negative square root of 3, done and done. Oh, yes. So I'm going to red box this. Red boxing it. That's right. Putting our answer in a red box. Thank you. Oh, you didn't get all of that box? Let me here. There you go. There's your complete box. Now, TI, what you got for me on this problem? Problem number 3. Problem 3, we'll have our next system. So we'll hit menu. We'll go to algebra, then solve system of equations, and you'll choose the first choice. We only have 2 equations, so click OK. And then we'll input our 2 equations. So the first one is y equals negative square root of x minus 1. So let's get our square root symbol here. And then we'll have x minus 1. And then we'll click into the second area to input our second equation. So we'll have the quantity of x minus 3, and that's going to be squared, then plus y squared. This equals 4. All right. And then we'll go ahead and hit enter. And our points of intersection are going to be at 1, 0, as well as 4, negative square root of 3. All right. And that's exactly what we got when we did it by hand, right? So now let's look at the graph. So for our first equation, we'll have the opposite of the square root of x minus 1. So go ahead and hit enter, and you'll see that your graph is here. And then we'll want to input the second equation. So due to the fact that we had to solve for y for each one of our functions, it turns out that I had to put a positive and negative version of that second equation. So I had a plus or minus the square root of negative quantity of x minus 3 squared plus 4. And so I had to break that up into two different functions to input it to get that full circle here, you see? So of course we had our f of 1 of x, which was the opposite of the square root of x minus 1. But now we have our circle and the square root function, and it shows where our intersections will be. And we'll find out exactly where those intersections are using the intersection function of the calculator. All right, so we'll hit menu, then go to intersection. So we'll then click on this one, and I'll say the lower bound is here, and it found an intersection. So we'll click there, and we found our point at 1, 0. And now for the second intersection, which looks like it's right here, right? Let's go ahead and hit menu, and then we'll go to analyze graph and go to number 4, which is intersection. And I'm going to choose the two graphs that I want to use, which is going to be this one as well as that one again. We'll hit lower bound. We'll move over. And once we have that intersection pop up, that tag, we'll go ahead and click on that. And this is going to be our point. And remember this point, that second value, this is the approximation of a negative square root of 3, that negative 1 and 73/100ths. So that confirms that our x and y value for that second point is correct. And that's going to be our results for problem number 3. Good old Texas Instruments. I appreciate your help on that problem. Let's look at problem number 4 now. We have the system that reads 3x squared plus 4y squared equals 16, as well as 2x squared minus 3y squared equals 5. What we'll do in this particular problem is I'm going to attempt to solve this using the elimination method. Oh yes. So this will be a different technique. The previous problems we used substitution, but in this problem right here, yeah, I'll be using the elimination method. And speaking of the elimination method, check out this video right here. On the elimination method, I'm in it. You know, it's me that's doing the video. I mean, if you want to spend more time with me, you could check out that video. I mean, and learn about the elimination method too at the same time. I mean, it's a win-win. You get me, you get the elimination method, you get Fort Bend Tutoring. Everybody's involved, and you are the honored guest, of course. All right. So check out that video. And we're going to get back to solving problem number 4 now. Thank you. So we'll begin the process by observing that if we were looking for the LCM of our x terms, looking at the coefficients 3 and 2, that LCM would be 6. And now looking at the y terms and looking for an LCM, we would have an LCM of 12. So my lazy side says I'm going to stick with the x terms because it has a smaller LCM. See, I want the numbers to be kind of small. So therefore, on the first equation, I'm going to be multiplying by 2. And the second equation, I'll be multiplying by negative 3. So we'll end up with a system that reads 6x squared plus 8y squared equals 32. Whereas the second equation reads negative 6x squared plus 9y squared equals negative 15. And then we'll be adding these like terms together. So we know that our x terms will cancel out altogether, right? And we now have 8y squared plus 9y squared, which gives us 17y squared. Then 32 minus 15 happens to be 17. Oh, do you see the beauty in this already? We're dividing both sides by 17. We'll get y squared equals 1. That's exactly what we'll get. So at this point, we'll be using the square root property. And if you need help with the square root, you know I got you. It's right here. It's right here. Thank you. Yeah, let's continue. We'll be taking the square root of both sides of the equal sign. And of course, using our shortcut here, we'll have plus or minus the square root of 1. And this gives us y equals plus or minus 1. Yeah. So our potential values of y are negative 1 and 1. Those are our potential values of y. So now we'll be plugging that into one of the original equations. So taking our potential values of y, negative 1 and 1, and plugging into one of our original equations, I'm going to choose the second equation. And I'm choosing the second equation because it has smaller numbers and I'm lazy. Thank you. So we'll plug in those values. Let's start with negative 1. And it'll be 2x squared minus 3 times negative 1 squared equals 5. So we want to solve for x in this case. So this gives us 2x squared minus 3 times 1 equals 5. This now gives us 2x squared minus 3 equals 5, and then adding 3 to both sides of the equal sign, like so. Our 3's will cancel out. We'll bring down 2x squared equals 8, and then dividing both sides by 2, we now have x squared equals 4, and then using the square root property on this, we'll have the square root of x squared equals plus or minus the square root of 4, which gives us plus or minus 2. So our potential points of intersection will be -2, -1, as well as +2, -1. So these 2 points are potential solutions to our original system. Now let's see what values of x we'll get when we plug in +1 into our second equation from the original system. So plugging in +1 into the second equation, we have 2x squared minus 3 times 1 squared equals 5. Well, this looks familiar, right? Because when you square the +1, you'll still get 1 as a result. So therefore, you'll have the 2x squared minus 3 equals 5, as well as needing to add 3 to both sides of the equal sign and getting 2x squared equals 8, dividing both sides by 2, like so. You'll have x squared equals 4, and then using the square root property, of course, you'll have plus or minus the square root of 4. And now x equals plus or minus 2. So because x equals plus or minus 2, our potential solutions from this equation will be -2, 1, as well as +2, 1. And then these two solutions, along with the previous two solutions, we'll need to test in the original system to see if they work. Remember, for a potential point to be a solution to the system, the solution has to make a true statement in every equation in the original system. Let's try testing out the first point in our original system to see if it gives us true statements in both equations. So we'll rewrite this as 3 times -2 squared plus 4 times -1 squared, and this needs to equal 16. We know that -2 squared is 4, and we know that -1 squared is 1, and this equals 16. So the product of 3 and 4 is 12, and 4 times 1 is 4. And the last time I checked, guys, 12 plus 4 equals a 16. So since 16 equals a 16, this works. However, oh, see, it's not in view, is it? There we go. It's in view now. So it definitely works in the first equation. However, it has to work in both equations. So let's check out that second equation now. So we'll have 2 times -2 squared minus 3 times -1 squared, and this should equal 5. So this gives us 2 times 4 after squaring the -2 minus 3 times 1 after squaring the -1, and this should equal 5. Well, 2 times 4 is 8, right? And we'll have 8 minus 3, and lo and behold, 8 minus 3 is 5, and 5 equals to 5. So therefore, this checks out, which means this first point of intersection works just fine. But if you've been paying attention to the system and our process, you should know that every x and y value will be squared. And because every x and y value when squared gives you the same result, which means that each one of these potential points will work in our original system. They have to work because the first one worked. All right. So therefore, this is our answer. We're looking at it. All 4 points are intersections, are solutions to the system. Red box it. Red boxing it, ladies and gentlemen. Done and done. Let's see what TI has to say about this. And so for our fourth problem, we'll go ahead and click Menu, Algebra. Go down to Solve System of Equations. Choose the first choice. We do have 2 equations in x and y, so click OK. And then in our first prompt, we'll type in 3x squared plus 4y squared, and this equals 16. And then we'll go ahead and click in the second prompt area there, that second box, and we'll type in 2x squared minus 3y squared, and this equals 5. From here, we will go ahead and click Enter, and that gives us our solutions. So notice that we have our first points, -2, -1, and then it goes on to -2, +1. From there, we can click on this arrow here to keep it going. How amazing is that? That is awesome. All right. So let's go ahead and see what the graph looks like. We'll click on Graph. As an alternative way to input conic sections, especially if you're not certain if it's going to be a hyperbola or an ellipse or a circle, what you can do is you can go ahead and go to Menu, then you can go to Graph Entry, and then from there go to Equation Templates, and then we'll choose to go to Conic and General Conic. So with that option, we won't have to solve for y and use the square root property in order to input the equation. Instead, I'll just put in that I had 3x squared, and then I had 0 xy terms, but I do have 4y squares, and then 0x as well as 0y, and then setting this equal to 0, we'll have negative 16 inputted for that last value, and then hit enter, and there you have your conic without having to go through the pain of having to solve for y. So I found that to be very useful. So I'll be inputting the second conic using that same process. So I'll hit menu, graph entry, then equation templates, and then I'll go down to general conic and type in my values for the coefficients. So I'll have 2x squared, I have 0xy, I'll have negative 3y squared, as well as 0x, 0y, and once again setting this equal to 0, this value will be negative 5 for that second equation, and then hit enter, and then we find it's a hyperbola, and we just need to find those points of intersection in this graph here. So we'll go to menu, we'll go to analyze graph, we'll go to intersection, and then we're asking which corner to use. We'll say we'll click in this first corner here, and then we found that this point will be negative 2, 1. So let's find the next intersection. We're going to menu, then analyze graph. We're going to intersection. It's asking us which corner. So we'll click here for the first corner, and then it found an intersection. So we'll click for the second corner, and it found that we have a point located at negative 2, negative 1. All right, let's find the other two intersections. Menu, analyze graph, intersection. First corner we'll put here, and then it found an intersection. So we'll click there, and it found that we have an intersection here at 2, 1. Next, we'll go to menu, analyze graph, intersection, and then it asks for a corner. So we'll go here and we'll drag it out till we found this other intersection. And now our fourth intersection is at 2, negative 1. And now we have verified all 4 points of intersection that we have in the system. And that completes problem number 4. All right, and finally we have problem number 5. And with problem number 5, we have x squared plus 3xy plus y squared equals 20. And in our second equation, we have xy minus y squared equals 0. We're going to take this second equation and we're going to use the zero factor property. Yeah, let's do that. If I have xy minus y squared equals 0, and then I factor out the GCF of y, that'll be y times x minus y equals 0. So what do we find by doing that? What do we learn from this? Well, we learned using the zero factor property that y equals 0 or x minus y equals 0, which means that when we solve for y here, with the negative y equals negative x and then divide both sides by negative 1 or multiply both sides by negative 1, that y equals x. Yeah, so being as though we know that y equals 0 or y equals x, let's go ahead and take these values of y and see what values of x we'll end up with, okay? When y equals 0, this first equation becomes x squared equals 20. So by solving for x using the square root property, we'll have the square root of both sides, and using our shortcut, we'll have plus or minus the square root of 20. When we simplify this, we'll have the square root of 4 times 5, which simplifies to give us plus or minus 2 times the square root of 5. So as potential points of intersection, we would end up with negative 2 square root of 5, 0, as well as positive 2 square root of 5, 0. So we already have 2 potential points of intersection. Now let's see what happens when y equals x. Replacing every y with x in our first equation, we would end up with x squared plus 3x squared plus x squared equals 20. From here, we would end up with 5x squared equals 20, and then we can divide both sides by 5 to end up with x squared equals 4. Using the square root property, we'll have the square root of x squared equals plus or minus the square root of 4, which simplifies to give us plus or minus 2. That means that our points of intersection would be negative 2, as well as 2, 2, recalling that y has to equal x. So you would end up with negative 2, as well as 2, 2. So that means that we'll be testing these 4 potential points of intersection in our original system. All right, so let's go ahead and test each one of these points in our original system. Let's start out with our first point, the -2 square root of 5 and 0. So plugging in our values, we'll have the quantity of -2 square root of 5 squared plus 3 times the quantity of -2 square root of 5 times 0 plus 0 squared equals 20. And this is what we have thus far. Simplifying this, -2 times the square root of 5 squared gives you 4 times 5 plus 0, which must equal 20. Well, 4 times 5 is 20, plus 0 still equals 20. So this checks out just fine. But the point must work in both equations. So let's try the second one. We would have -2 times the square root of 5 times 0 minus 0 squared equals 0. And once again, 0 minus 0 equals 0. That checks out. So the first point works just fine. And you know what? Looking at our second point, 2 square root of 5, 0, this will also work as well due to the fact that the 2 square root of 5 will be squared. And of course, that second value being 0 will wipe out the other terms in both equations. So the first point and the second point work just fine. Now let's check out the last 2 points. With our last 2 points, we have -2 squared plus 3 times -2 times -2 plus -2 squared, and this should equal 20. So we know that -2 squared is 4, and then 3 times -2 times -2 will give you positive 12 plus 4, and this should equal 20. Well, 4 plus 12 is 16, and then 16 plus 4 will give you 20. So that means that the first equation gives us a true statement, so that works just fine. Once again, it must work in every equation. So let's see how our point works in the second equation. So we'll have -2 times -2 minus -2 squared equals 0. We know that -2 times -2 is 4, minus -2 squared is 4, and 4 minus 4 is 0. So that checks out, and that works just fine. Well, seeing how that point works out, you guessed it, 2 will work out just fine as well. And so therefore, all 4 potential points are solutions to our system. So our solutions for problem number 5 are going to be -2 square root of 5, 0, 2 square root of 5, 0, -2, as well as 2, 2, and red box it. That's right. All 4 points are solutions to problem number 5. Done and done. And let's have Texas Instruments and the TI-Nspire CX CAS show us if we're right or wrong. Let's check it out. For problem number 5, we'll input our system by clicking Menu, then going to Algebra, then Solve System of Equations. We have 2 equations in variables x and y, so we'll click OK. In our first equation, we'll have x squared is going to be plus 3x, put a multiplication symbol between the x and y variables. Then you'll have plus y squared, and this equals 20. So then clicking in the second prompt area, we'll have x, use your multiplication symbol between the variables. This is going to be minus y squared, and this equals 0, and then hit enter. And we have our solutions. We have -2 square root of 5, 0. We also have -2 and -2. Then going from there, we'll have 2 and 2. And we also have 2 square root of 5 and 0. So these are all 4 of the points of intersection that we found when we did it by hand. Love it. Let's go ahead and check out the graph. So from home, we're going to go to graph. And then we want to go to menu. And from here, we want to go to graph entry. And then because this is going to be a conic section, we'll go to equation templates and go to conic general. And we'll be able to type in that we have 1x squared, we have 3xy, we have 1y squared, we have 0x terms, 0y terms, and we have -20 after setting this equal to 0. And then you'll hit enter. And this will give us our graph of the first equation. So with the second equation, we're hitting menu. We're going to graph entry, then to equation templates, and then we'll go to conic general. Click enter on that. we have 0 x squared terms, we have 1 xy term, we have -1 y squared terms, you have 0x terms, 0y terms, and 0 for our constants. So then we'll hit enter. So now let's find our points of intersection. So we'll go to menu, we'll go to analyze graph, we'll then go to intersection, and the corner that we're going to choose here is this corner, and then we'll drag that, and we found an intersection here. So clicking enter, and we end up with this -4 and 4700 0. So this is going to be our -2 square root of 5 0 point that we have. Now let's find some more. Menu, analyze graph, intersection. So choosing a corner here, we'll go here for the first corner, and we found another intersection, and this gives us the point -2, -2. I'll put that there. And our next intersection, we'll have menu, analyze graph, intersection. We'll create the corners where we should find our intersection. I will put a point there. We found an intersection there, and we found a point at 2, 2. And finally, for our last intersection, menu, analyze graph, intersection, and then creating that box area that we'll use to find our point of intersection. I'll click here, and then it found an intersection, so we end up with the +2 square root of 5 0 point, and this confirms our points graphically for our problem number 5 using the TI-Nspire CX CAS calculator from Texas Instruments. And that's the last problem, guys. Yeah, thanks, TI. All right, ladies and gentlemen, that is going to complete our video on nonlinear systems. We want to once again thank our sponsor, Texas Instruments, for their assistance in this video, and be on the lookout for a giveaway video on the TI-Nspire CX CAS calculator that you saw used in this video. And as always, please rate, comment, and subscribe. And if you're able, please donate, as that helps us bring you more free math tutorials from me, Mr. Whitt, and Fort Bend Tutoring. Peace.
Thanks for watching. We feel great knowing that you got some help and you're safe and sound. Now, if you'd be so kind as to like this video, subscribe to our YouTube channel, Fort Bend Tutoring, and like us on Facebook, we'd be much obliged.